So let's just first review the Ray theorem for a fiber bundle. Okay. Let pi from E to B be a fiber bundle with fiber F. And we assume that the base is simply connected. B, okay? And then we also assume that the cohomology of the fiber in each dimension is free of finite rank. Okay? Yeah, these are just to make the statement of the theorem a little simpler. Okay? So then there exists a spectral sequence ER dr with E2 being the tensor product of the cohomology of the base with the cohomology of the fiber. Okay, and this is an equality as rings. Okay? So, in other words, E2 has a ring structure, and it's given by the tensor product. Okay? See, this is the cohomology. This cohomology ring is a ring. This is also a ring, so the tensor product is a ring. And E2 has the ring structure of the tensor product. Okay? So there's this spectral sequence. And then on the infinity term, you have a filtration. Di on the filtration is on the cohomology of the total space. Such that the E infinity term is the associated graded group of the cohomology of the total space. Okay? Okay, so that's the theorem. And moreover, so dr goes from ER to ER. Okay? And each ER has a ring structure because E2 has a ring structure. So the cohomology of E2 will have a ring structure. So E3 has a ring structure, and so on. You see, every ER has a ring structure. And then dr, it goes from a ring to a ring, and it is an antiderivation. Okay? So an antiderivation, what that means is that i.e. So dr of the product of two things. Okay. Now a derivation would be dr alpha beta plus alpha dr beta. Okay. So that would be a derivation. But an antiderivation means that when you move dr across over alpha, you multiply by -1 to the degree of alpha. Okay? So dr satisfies that property. Yeah?
I forgot the gradient group, the relation of gradient group and filtration. What is the relation?
Oh, yeah. This is the associated graded group. Okay. So you have a filtration on the cohomology of Taylor space. That means, okay, I'm going to put a star here. Okay. So star means, okay, you have a filtration is a decreasing sequence of groups. So you start with the cohomology of the total space, and that's your D0. Okay, and then you have D1, D2. Okay, and then it ends somewhere. Okay, it might not be a finite filtration. Yeah. The end. Okay. And then when you have a filtration, you have an associated graded group. So this would be D0 over D1. Yeah, so then the associated graded group is the direct sum of all the quotients. So it's D0 over D1 plus D1 over D2 over D3. Okay, yeah. Okay, now, because like all of these groups, ER are bigraded, so you have 2 degrees, and yeah. And we represent, each ER by a grid like this. So ER, it's a direct sum of all of these boxes. ER, PQ. Where PQ are greater than or equal to 0 because we are only working with a first quadrant spectral sequence. And
so it's E2 or ER?
Pardon? Oh, sorry, this is ER. Yeah, every R looks like that. And you have a bi-degree PQ, but you also have a total degree. You can sum up these. So let's see, 0, 1, 2, 3. So for example, if you want to look at total degree 2, then you have 3 boxes, right? This is 0, 2, 1, 1, and 2, 0. Okay. So these 3 boxes have total degree 2. Okay? Yeah. So you can look at just that total degree, and if you just look at Hn of E, that's a single degree, the filtration induces a filtration on this, okay, just by taking the intersection. So I'm going to say this, yeah. So let's see. Let's put it over here. So there is an induced filtration Vi intersect Hn of E, okay, for each n. And the induced filtration starts with D0 intersect Hn of E. I'm going to say, just to simplify the notation, I'm going to write Hn to mean Hn of E. Okay. So this is Hn, and then it contains D1 intersect Hn, contains D2 intersect Hn, and so on, okay? And then when you take the associated gradient, you're taking this quotient, and this quotient, okay? Now, if you compare the bidegrees, okay, so this one, you see, the filtration is filtration by P, okay? So this one is going to give you the box whose P is 0. So it is E infinity 0 n, and this is E infinity 1 n minus 1, E infinity 2 n minus 2, and so on, okay? So if you know E infinity, then you know these quotients. And it doesn't necessarily give you this, because it's an extension problem now. So that, see, if you stop, for example, if you have a group G, and then you have a filtration, say Z2, 0, okay? And you know the quotients. See, the spectral sequence gives you E infinity, and E infinity gives you these quotients, okay? But what you want is G, but what this filtration says that is that you have a subgroup of G, Z2, so G2, so Z satisfies, it has a subgroup. And the quotient group is Z2. So Z satisfies this exact sequence. Now, can you tell me what G is? What is? These are abelian groups.
Either Z4 or Z2 product Z2.
Yeah, you see. Then, so what is G? Well, so G could be it could be Z2 plus Z2, okay, because this has Z2 as a subgroup, and then the quotient is Z2 again. Or it could be Z4, okay, the cyclic group with 4 elements, because that also has Z2 as a subgroup and Z2 as a quotient group. Okay? So when you know these quotients, you don't necessarily know what G is. You see, there's an extension problem. So the spectral sequence may not give you the answer. It may just give you a possibility, a set of possibilities as the answer. However, we know that, say, if you have an exact sequence from A to B to C, an exact sequence of abelian groups, and C is free, then what can you say? So this is an extension problem. What can you say about B? B has a subgroup A, and its quotient by A is C. Okay? In general, there are many different possibilities for B. But if C is free, then, have you seen this before in algebra? Now, if C is free, then you can define, because this map is surjective, okay? So if C is free, there is a map going backwards so that the composition is the identity. See, if C is free, then you have a section. And in that case, B will be isomorphic to A direct sum C. Okay? So this is a lemma in algebra. Okay? And so, like, if your quotient is free, then you can determine what the middle group is. And so that happens a lot when we do spectral sequence computation. And so we can actually get the answer. Okay? So let's do an example. Then you'll see how it all works. Yeah. So I think maybe I'm going to keep the Ray theorem up there. So let's calculate the cohomology of CP2. Okay. Now we need a fiber bundle. So is there a fiber bundle involving CP2? Do you know of a fiber bundle that has CP2 in it? Yeah. How is CP2 defined? It's the quotient of Yeah, it's a quotient of C3 minus the origin under C star, but it's also the quotient of, the way we define it was, it's a quotient of what? S5, right? The unit sphere in C3. It's a quotient of S5 by an action of S1. So you have this fiber bundle, okay? S5 is a fiber bundle over CP2 with fiber S1. And we can apply a spectral sequence to this. Okay? So the spectral sequence, the ray spectral sequence of this fiber bundle has E2, the cohomology of the base tensor with the cohomology of the fiber. Oh, yeah, S1. And, now in order to apply the ray spectral sequence, we first have to make sure that the base is simply connected. Okay? Yeah. So let's see, how can we prove that the base is simply connected? How can you calculate the fundamental group of... Yeah, you can use the homotopy exact sequence of the fiber bundle. Okay, so this is if CP2 is simply connected. Okay? So we first have to show that CP2 is simply connected. Okay, so let's do it here. Okay, so let's show that CP2 is simply connected. Okay, so by the homotopy exact sequence of the fiber bundle S1 to S5 to CP2, we have this exact sequence, pi q of, well, I only want to do pi 1, so I'm going to start with pi 1, right? The pi 1 of S1 goes to pi 1 of S5, goes into pi 1 of CP2. That goes to pi 0 of S1, and then pi 0 of S5. Okay? Now both S1 and S5 are connected. So pi 0 is a single element. So this is an isomorphism of set. Okay? And that means this map goes to 0, right? Because the image of this is kernel of this. So yeah, so and pi 1 of S5 is 0, so we get an exact sequence from 0 to pi 1 of CP2, and then it maps to 0, because this is an isomorphism. And so that says that pi 1 of CP2 is 0, okay? Okay, so it's simply connected, and we can apply the ray spectral sequence, and we get this E2 term as a tensor product. So let's see. Now let's draw the E2 term. Yeah. Okay, so E2 is this page. Now, along the base, it's the cohomology of CP2. And along the fiber, you have the cohomology of S1. Now, so in degree 0, this is, because this is connected, you know what H0 is. H0 is Z, okay? And H0 of S1 is also Z. So it has a generator. The generator is 1 tensor 1, but I will write, so the notation. So if I have something like U tensor X, I'm going to write that as UX, okay? So 1 tensor 1, I write as 1. That's the generator in H0. And then this column, right, it's, so the first, the zeroth column is it's HQ, no, it's E2 0Q, right? The zeroth column is that. And that's H0 of CP2 tensor with HQ of S1. So it's Z tensor HQ of S1. Okay, and we're doing tensor product over Z. So this is just HQ of S1. Okay, so this column is just the cohomology of S1. And therefore, you know that it has, in degree 1, it's got a generator X. And then it's all zeros, right? So we have this much now. That's E2. Now let's look at the differentials. D2. So D2 is going to start here, and where does it go? You know, D2, how far does it go down? 1. And it goes across 2. So this is going to go down. 1 go across 2. It will go here. But everything is 0 outside the first quadrant. So this D2 is 0. Okay? And then the D2 will send this X to here. Okay. And then here is 0, so yeah, so this will be 0 anyway. Okay. Yes. And yeah, we don't know what this is. But, okay, so if you apply D2 to this picture, then you get E3, right? Yeah, so let's see what E3 looks like. Okay, I think I'm going to now finally erase the race theorem.
Maybe include the right upside.
Pardon?
JK
I can use that more. Right, good. So let's put this back. Okay, so that's E3. Now, you know, if it's 0 already, then when you take the cohomology, you will always get 0. So I know that E3 will have these 0 boxes. Okay. That's Q, that's P. Now let's look at D3. So D3, if it starts here, it's going to go down 2 and go across 3. So it's going to go there. And that's going to be 0. And this one, if it starts here, it goes down 2 and it goes across 3. So it'll go here. And that's also 0, right? Because it's also below the first quadrant. Okay? And what if it starts here? It's going to go here. But the domain is 0, so it has to be 0. So what can you say about D3? It's always 0, right? Because if it starts on the 0th row, it's going to go below the first quadrant, so it will be 0. If it starts on the second row, the first row, it's going to go below the first quadrant, so it will be 0. But if it starts on the second row, since the second row is already 0, it will be 0. So D3 is 0. Now, if the differential is 0, what is the cohomology? It's the original group, right? So D4 E4 is the cohomology of E3 with differential D3. And since D3 is 0, this will be E3. So E4 is the same as E3. What about E5? Same as E4, because you see, you have only 2 non-zero rows, so D4 will be 0 also. Okay? So in general, D3 is D4 is D5 is D6, and they're all 0. Okay? So yeah, so let's go back here. Okay, so E4 So E3 is going to be equal to E4. And E4 will be equal to E5, equal to E6. They stabilize after E3, and that is what is called E infinity. Okay? Now, E infinity is the associated gradient of the cohomology of the total space, which is S5. And the cohomology of S5, you know already, right? So what's the cohomology of S5? The cohomology of S5 with integer coefficients. Yeah, it's z in degrees 0 and 5, and it's 0 otherwise, right? So do you know how to compute the cohomology of S5? Like,
As a seated complex. As a seated complex, you just glue a five-dimensional disk to a point.
I see. Yeah. Okay. Yeah, okay, that's one way to compute it, right? You can compute it as a CW complex. And it has one cell in dimension 0, one cell in dimension 5. Right, yeah. What's another way to compute it? Yeah, you can also use the Meyer-Vittorov sequence. You have an upper hemisphere and a lower hemisphere. And the equator is S4. So you can do induction that way also. Okay? But anyway, so we know that the cohomology of S5 is Z for n equal to 0 and 5 and 0 otherwise. Okay, so we have a filtration on H5, on H5 of S5. Okay, there is a filtration. H5 of S5, which is D0. It contains D1, contains D2, contains D3, D4, D5. So you have a filtration on H5, okay? And this box is E infinity 0, 5. This one is E infinity 1, 5, 1, 4, and then this side. This one is E infinity 2, 3, E infinity 3, 2, E infinity 4, 1, E infinity 5, 0. Okay? So the spectral sequence will give you these quotients. Now, okay, by E infinity, let's see. So E infinity is the same as E3. Right? Okay. So I know that E infinity is the same as E3. And so it looks like this. There are only two non-zero rows. Zero, 1, 2, 3, 4, 5. Yeah, so everything here is 0. Let me see. CP, we're doing CP2, right? Yeah, so CP2, that has real dimension 4. So the cohomology is going to be 0 from degree 5 onwards, right? So we only have these boxes that can be non-zero, okay, in E infinity. Now, we are looking at degree 5. So the filtration is here. Okay, so now we already know that these boxes are 0. So there's only one box that could be non-zero. This box in degree 5. See, 0, 5 is 0. 1, 4 is 0. 2, 3 is 0. 3, 2 is 0. 3, 2. It's only 4, 1 that could be non-zero. 5, 0 is 0. Okay? And this is Z. So you see, well, since all these quotients are 0, yeah, Z is equal to this, and then the quotient is 0, so this guy has to be Z. Okay? Okay, so that means it's Z here. Z. Okay? And then in the other degrees, everything is 0, right? Because the cohomology, except for degree 0. So there's a Z here also. Okay. But in degree 1 and 2 and 3 and 4, the cohomology of the total space is 0. So all these boxes are 0. And now, that's E infinity, but it's also E3, okay? And then where is my E2? Oh, here's my E2. So when I take the cohomology of E2, I have to end up with this picture. So let's look at this box. Now, if there's something in there, yeah, you see, if there's something here, let's say, call it Y, okay, then what is D2 of Y? What's D2 of Y? 0, right? Because D2 of Y is going to go here. So Therefore, D2 is in the kernel. So, sorry, Y is in the kernel of D2. Okay? And then, can it be the image of something? But D2 is going to come from here, from this box, which is 0. So the image from this box to this box is 0, right? And if you have a Y here, it will be in the kernel. And so it's going to survive to E3. If you have a Y here, that Y is going to appear here. Okay, but it's 0 here, therefore it can't have a Y here. So this box has to be 0. Okay. What about this box? Let me see. No, just a minute. What? Yeah, if I know that it's 0 here, what's here?
Still 0.
Why is it 0?
It's divided by the tensor product.
Yeah, because it's a tensor product. E2 is a tensor product, okay, of the base and the fiber. So if it's 0 here, then this would have to be 0 tensor something, so it will be 0. Okay, so if E2 of 1, 0 is 0, then E2 of 1, 1 so then this is going to be H1 of CP2. E2 of 1, 1 is H1 of CP2 tensor with H1 of S1. So it will be 0 tensor with H1 of S1. And it will be 0. Okay? So this box is 0. Okay? And then, now let's look at this box. Could it be 0? Like if this box is 0, then what can you say about this X? It will map to 0, therefore it's in the kernel of D2, but then the image going into that box is always 0, so it will survive to E3. If it survives to E3, it's going to show up here, but here is 0. So it cannot survive to E3. Okay? You have to kill this X. How do you kill this X?
So the D2 of X wouldn't be 0.
D2 of X has to be non-zero. Okay? So since X does not survive to E3, in order to kill it, D2 of X must be non-zero. Okay? So that X is not in the kernel of D2. And so let U be D2 of X. So you know that there's a U here. Okay? And there's nothing else. Because if you have anything else, it will survive to, it will survive to E3. Now this U doesn't survive to E3 because it's killed by X. So U is in the kernel, but it's also in the image of X. Therefore, cohomology is 0. Okay? So you need a u there. If you have a u here, then what do you have here? Ux. You have the tensor product ux. Okay, and then what's here? 0, because anything here will be in the kernel, and it's going to come from this box. So anything here will survive to E3, but that box is 0. So this has to be 0, and then this has to be 0, okay? And then this comes from Ux. Okay? So V2 of Ux is, because you have an antiderivation, you have V2 Ux plus minus 1 to the degree of U V2X, okay? Now V2U is 0. V2U is 0. And degree of U is 2, so that's just minus 1 to the 2 is 1. And then you have U, and then D2X is U, so you get U squared, okay? So in this box, you have a U squared. And you have nothing else, because anything else will survive, okay? And then here you have U squared X. And then, let's see, 0, 1, 2, 3, 4, 5. Oh, and then here is 0, right? Because the dimension of CP2 is 4. So this is what D2 looks like, okay? This is what D2 looks like. And that says that the cohomology of CP2, so we have the cohomology of CP2. So the cohomology of CP2 is, it's Z in degree 0, and then degree 2 you have a U, and then in degree 4 you have a U squared. Okay. And so you can write this as this the polynomial ring generated by U, and then you set U cubed equal to 0. Okay. So that's the cohomology ring of CP2. Okay? Okay, I'm going to stop here, and you can see that you can use the same method to calculate CP3, CP4, CPn, and CP infinity. Okay? So, well, that will be your homework. Now, I realize now that problem set 1 was probably too long, you know. There are too many problems. From now on, I will just assign 5 problems in each problem set. And so, yeah, I have problem set 2 here. Okay, I'm going to make copies, and I'll give it to you after a 10-minute break. So we'll start again at 35 after 4. Okay? Yeah. Okay, good. Copia pronto.